All right, so we're now in lecture 2 of 124105, where we will learn about electric field. So we will define what an electric field is and how to calculate an electric field. But electric fields are very much closely related to electric forces, which we've learned yesterday. So yesterday we started the course by talking about charges. What are the properties of charges? And then we saw the rolling can demo, right, with demonstration with the balloon making the can move. And that is because charges can exert force on each other or on other charges. And the magnitude or how much force a charge exerts on another is given by Coulomb's law. And we had an example yesterday of how to use Coulomb's law to calculate the magnitude of the force. The direction of the force is obtained using dichotomy property, where opposite charges attract and like charges repel. But we left the lecture yesterday looking at this example of when you have multiple charges present and we want to find the force experienced by one charge because of the presence of the other charges. So let's look at how we can solve this example here, where you have 4 charges, 3 of which are positive, 1 is negative, and we want to find the net force experienced by charge Q2, which is the one at the upper right corner. Yesterday, we already drew the electric field, the free body diagram showing the forces acting on charge Q2, right? So we draw these 3 forces acting on charge Q2 because of the other charges around itself. And so today we will look at how we can find the answer for the force experienced by the charge. Just looking at the free body diagram, you see a diagonal force here, which tells you that there has to be X component and Y component present in the net force. So how do we do that? I've laid down some guidelines, like some steps that you can follow when you're solving for forces. And that go essentially the most important is to draw a free body diagram, because from there, that's where you get the direction of the force, and the magnitude is calculated by Coulomb's law. So let's apply that to this example, right? So the Coulomb's law gives you the magnitude for the force. And yesterday we've seen if you have more than 2 charges, then you look at 2 charges at a time, because Coulomb's law only involves 2 charges at a time. Right, so and just a reminder here, we'll use the unit vectors to indicate the direction according to the direction of the forces we've drawn. Okay, so let's consider the force that charge Q2 experiences because of the presence of charge Q1. Right, Coulomb's law says it's KQ1 Q2 times Q2 over R squared. Right, so Q1 and Q2, they're both capital Q. Right, the charge is given as capital Q, and the distance between the 2 charges, that gives you R. Okay. Yeah. So they're at the corners of a square. So if this is S, then the distance between Q2 and Q1 is also S. And don't forget, there's a square in the distance, so that's S squared. So for the magnitude, you get that using Coulomb's law. And for the direction, you get that using the direction of the force you've drawn using, dichotomy property, like charges repel, opposite charges attract. So that's I have. You do the same thing for charge Q4, right? Let's do charge Q4 first, because it's just along the vertical or the y-axis. So again, you do Coulomb's law for the magnitude, giving you KQ squared over S squared. And then for the direction, the force by charge 4 on 2 is directed upwards. So that gives you a positive, sorry for the typo there, positive J hat or a positive Y direction. Right, so relatively straightforward if you have horizontal or vertical forces. Now let's deal with this diagonal force, because that's the force should act along a line joining the 2 charges. between Q3 and Q2, the force will be diagonal. Okay. When you calculate for the magnitude, okay, again, we are just looking at this equation, Coulomb's law, and then just calculate them as K times the charges multiplied together. So that's still K times Q times Q. All right, really important to disregard the sign of the charge when you're using Coulomb's law, because the sign comes into the direction that you've determined. And so when I calculate Coulomb's law, I did not include negative for the charge of Q3. Okay. Right. And then the distance is this hypotenuse, is the hypotenuse of this right angled triangle. So both sides of the triangle is S. So therefore, this hypotenuse is square root of S squared plus S squared. And then don't forget there's a square in the distance as given in Coulomb's law. So then you will get the magnitudes of the force on Q2 because of Q3. Right, for the direction it's, you have a right angle triangle, so this angle will therefore be 45 degrees. So it's 45 degrees relative to the positive X direction, or I hat. Okay. Right, whenever you have a diagonal vector, you can decompose that vector into its X and Y components. So meaning F23 will have an X component and a Y component, right, with the angle of 45 degrees. That allows us to find the X component cosine theta. So remember our mnemonic. SOHCAHTOA, if you're looking at the adjacent side, then you get the cosine of the angle times the hypotenuse. X component is the adjacent side to the angle. Likewise for, right, so you can simplify this. Cosine 45 divided by 2 will give you 0.4. Okay, and the direction, of course, will be the direction of the X component of your diagonal vector, which is pointing to the left, hence negative I hat. Right, and then for the Y component of this diagonal vector, our mnemonic says you're wanting to find the opposite sides of a right angle triangle, hence you use the sine of the angle theta times the hypotenuse. And the hypotenuse is the force 2,3, which you've calculated as the magnitude of the force. Hence you have sine 45 degrees times the force 2,3, which serves as the hypotenuse. The direction will be the direction of the Y component of the diagonal vector. It's pointing downwards, therefore negative J hat, which we can then simplify. Sine 45 divided by 2 gives you 0.4. So you have now the Y component of the diagonal force F23. Are we okay so far? Yeah. Right, so we have these 4 vectors, okay, F21 along the positive X, F24 along the positive Y, F23X along the left or negative X, and F23Y along the negative Y or downwards. We then, if we want to get the net force, we then have to add the vectors. Okay, so add all the X components together and add all the Y components together. So when you do that, right, essentially you have these 4 vectors. I've just redrawn the free body diagram. From this free body diagram, I've redrawn it so that the diagonal F23 has its X and Y components, allowing me to see clearly that to get the net force along the horizontal, I subtract F23 from F21, okay, which is what I've done here. The direction is along the x-axis, and therefore I get this result for the net force along the axis. I do the same thing for the y components. So my redrawn free body diagram shows me clearly that F24 is positive, F23y is negative. Hence, the net force along the y is F24 minus the y component of F23. Right? If you simplify this, that also gives you 0.6 kq squared over s squared, direction along the j or vertical. Right, so then you have both the net force along the x-axis and the net force along the y-axis. That gives you now the net force of experienced by charge Q2. It has x components and y components, and you can stop here as your final answer. Or if you want to get magnitudes and direction, you can use Pythagoras theorem because you know the x component and the y component to get the magnitude of f, and for the direction use the tangent theta function. Right, but I will accept, as I said, I will accept this as your final answer, except in the assignment, in the mastery test online assignment, if they specifically ask you to put the magnitude and direction, then you'll have to do this extra step. Right, any questions about this example? It's also sort of a refresher on vectors and vector components. Very good. Okay, and we can move on, right? So we've seen here a charge can exert a force on another charge, even without touching each other, right? The demonstration yesterday with the balloon attracting the can, causing it to move, it's a classic example of what we call action at a distance, because normally we know that if I push on an object or I pull on an object, I have direct contact on the object, causing that object to move. That's quite intuitive, right? You can easily understand that. But the fact that the balloon made the can roll without touching it, it was a spooky concept. It was a spooky concept in the 19th century, in the time of Newton and Einstein. And so they probably thought it was witchcraft or something, something magical. And so to try to explain how a charge can cause another charge to move without direct contact, they created the concept to try to explain what they observed. And the concept they created was what they call electric fields. Okay? So electric fields is a concept that involves charges exerting forces on other charges. Incidentally, students nowadays find this concept difficult. It's the fault of Newton and Einstein. Don't blame me. But so then we can define the electric field as a space surrounding a charge. And it's through the electric field that a charge can exert a force on another charge. So we can think of the electric field as the intermediary for which a charge can cause another charge to move. Yeah. Mathematically, it's defined as force per unit charge, okay? Because if you think of the concept as an intermediary for the charge to exert a force, then mathematically the definition for electric field should involve the force and the charge, and it's defined as the force divided by the unit charge, or F over Q. Okay, moving from Coulomb's law. So Coulomb's law, you have KQ1 Q2 over R squared, right? If you define electric field as force divided by charge, then you're essentially dividing KQ1 Q2 with Q, and therefore in the definition of the electric field, you only need a single charge in order to have an electric field. right? So that you see the difference here. This is force, Coulomb's law. Right? So for you to have force, you need two charges because one charge will exert a force on another charge. Whereas for an electric field, you only need a single charge in order to have an electric field. So you can think of it as, for example, a negative charge generating an electric field around itself. Okay, so you can have an electric field even if you have a single negative charge. Or likewise, you have a positive charge, a single positive charge generating an electric field around itself. Okay, and if you bring these two charges close or within the vicinity of each other, then these two charges can exert force on each other via the electric field that they've created around themselves. All right. Cool. Does that make sense? Is it okay so far? Right. So electric fields, they're invisible, and that's why we cannot see how the balloon is able to make the can move. Since they're invisible, they're difficult to visualize. So Michael Faraday was the person who created a way to sort of draw electric field lines, and he called those electric field lines. I mean, he conceptualized electric field lines as a way of drawing electric fields and allowing us to visualize the electric fields generated by charges. And when drawing electric field lines, we follow certain rules. So the first one is that the direction of the electric field is always tangential or tangent to the electric field line. So say, for example, this is your positive charge. You draw your electric field lines as straight lines coming from the positive charge. If you want to find the direction of the electric field, for example, at point P, then you draw a line that's tangent to the electric field line. Here it's easy, it's a straight line, but of course, if you have a curved electric field line, so for example, this is your field line, and you want to find the direction of the electric field at this point, then you draw a line that's tangent to that point, and you say that the direction of the electric field is to the right, or positive I hat, because the tangent to that electric field line at that point is pointing to the right. Okay, the electric field lines originate from positive charges and terminate at negative charges. So you see here two different charges. Notice how the arrows are pointing away from a positive charge, whereas it's pointing towards a negative charge. Right, the density of the electric field lines tells us how the magnitude or how much electric field is present. So the denser the field lines are, the higher the electric field at that position. So here you can say that there's a high magnitude of electric field, whereas here the electric field is quite negligible compared to, because you almost don't have electric field lines at this point. So you can say the electric field is negligible, maybe almost zero. Whereas at this point where you have a lot of electric field lines, you can say that you have a high magnitude of electric field at that point. And finally, electric field lines should never cross because electric field lines determine the direction of the electric field. So for example, this is your electric field line 1 and electric field line 2. If they cross at this point, then that gives you two directions for the electric field at that point, okay, which is not allowed. And that's why electric field lines never cross. right? So you can always refer to these rules as we move forward and study electric fields, but just quick conceptual tests to sort of emphasize the concepts. So here you have two charges, a red one represented by red and green dots. So which one is positively charged and which dot is negatively charged? Right, you can check the direction of the electric field lines. Right? Electric field lines go from positive to negative, hence the red dot should be positive and the green dot should be negative. Right? Straightforward. Okay, which of the charges has a greater magnitude? Yeah, all right. So we said that the denser the electric field lines are, the more electric field lines you have, the greater the electric field, and electric field is generated by charges. So the bigger the charge, the more electric field you create, and therefore you have more electric field lines coming from this bigger charge and less electric field lines terminating on this smaller charge. What's the ratio of the charge of the two charges? It's sort of 1-to-1. Okay, so if you can see here, you have 12 electric field lines coming out of the positive charge, 6 electric field lines entering the negative charge. So the ratio of red to green is 12-to-6 or 2. It gives you an idea that the red charge is double the green charge. So if the red charge is, for example, 2 coulombs, then the green charge should have a charge of 1 coulomb. So sort of the ratio of electric field lines to the charge is sort of has a 1-to-1 correlation. Right, relatively straightforward so far, I hope. Okay, so now that we've established how to draw electric field lines, let's practice how to calculate the electric field. So you have here two charges, positive charge plus 2q and a negative charge minus q, right? As we've learned, this plus 2q charge will generate an electric field around itself. This negative q charge will generate an electric field around itself. We want to find what is the magnitude and direction of the electric field at point P, which is to the left of both charges. All right, the approach you do here is exactly the same approach we did with using Coulomb's law, because in essence, the equation for the electric field came from Coulomb's law. So you calculate the magnitude of the electric field using the equation, disregard the sign of the charge, because the sign of the charge gives you the direction of the electric field. Right? So you use the sign of the charge to find the direction of the electric field, but you use the equation to find the magnitude of the electric field. So you have two charges. Therefore, you calculate the electric field generated by each charge one by one. All right. So for this charge 2q, the magnitude will be k times the charge, which is 2q. Okay, so 2q is the charge divided by r squared. R is the distance between the charge and the point where you want to find the electric field. Okay, so the charge is a distance x away to the point where you want to find the electric field. Hence, r will be equal to x. That's the distance between the charge and the point. And don't forget there's a square there. Okay. So magnitude is 2kq over x squared. For the direction, okay, this is where you use electric field lines to find the direction. So we know electric field lines originate from positive charges. So if you draw the electric field lines of this +2q charge, you have electric field lines coming out of it like this way. Of course, the electric field will permeate through space, right? So the electric fields will permeate through space, passing through point P. And so at point P, the direction of the electric field is pointing to the left, and that's why you have this negative I hat direction. Right? Okay. Right, so this is the electric field for the charge +2q. We do the same strategy for the charge -q. The magnitudes will be k times the charge. Okay. Q is the charge. Again, we disregard the sign. It's a -q, but when you're calculating the magnitudes, just use the absolute value, disregard the negative sign there. And then R in your equation is the distance between the charge that's generating the electric field and the point where you want to determine the electric field. So that's 2x, right? It's x between these two charges and x between the middle of this charge and P. Hence, the distance is 2x. Don't forget there's a square, so that's 4x squared. And for the direction, this is a negative charge. So the electric field lines will point towards the negative charge. Okay, of course, the electric field again permeates throughout all space. So at point P, you will have, maybe I should have used a different colored pen. All right, so for this, these are the electric field lines for the -q charge. If you extend this electric field line, it will pass through point P, right? That's this electric field line extended. So at point P, the point where you want to find the electric field, you can see that the electric field line that belongs to the -q charge is pointing to the right, and hence the direction is +I hat. Right? Okay, is that clear how to find the direction of the electric field? Okay. Yeah. Then finally, to find the total electric field, just do vector addition for these individual electric fields. One is negative, right? So this 2kq/x² is negative. This kq/4x² is positive, giving you that answer for the net electric field. Good. Any question about this example? Right, in the workshop, you'll solve, like, we'll add one more charge and you'll solve for 3 charges, but the steps should still be the same. Right, so we see here that you can have an electric field at any point in space, even if you just have a single charge. But if we now want to find the force, say it's the same set of charges, it's the same point P, but now we put a charge +q at point P, and we want to find the force that this charge that we put at point P experiences because of these 2 charges, +2q and -q. So how do we solve for the force experienced by this +q charge at point P? Right, we've learned Coulomb's law, so you should be able to solve this using Coulomb's law, or you can also use the electric field that you've solved previously. We've determined that at point P, the electric field is this one. -7/4 kq over x squared I hat. And then use the definition for the electric fields. Yeah, this comes from electric field is force per unit charge. And therefore we can solve for the force by multiplying the electric field with the charge that you put at point P. Hence, the force is equal to -7/4 kq squared over x squared I hat. Right. So for force, when you're solving for force, you need two charges to exert force on each other. For the electric field, a single charge can generate an electric field. If you have two charges, of course, this electric field is the combined electric field generated by each charge. All right. Any questions? Good. Right. So this is how you solve a charge, the electric field by a single point charge. But in reality, objects are extended, right? Of course, if we can always assume that an object acts like a point charge, and that makes us calculate the electric field of that object, particularly if you're looking at electric fields at a very far distance. But in general, objects are extended. And so we need another way of solving the electric field, and this is called Gauss's law. So Gauss's law is used to solve the electric field of highly symmetric charge distributions. The key there is highly symmetric charge distribution. So in this course, we will actually just look at these three distributions. If you have a line charge, if you have a sphere that is charged, or if you have a plane, a sheet of paper that is charged, for example. And so Gauss's law, the reason why we'll only look at symmetric distributions is because Gauss's law involves an integral. Gauss's law is defined as this. The electric flux phi subscript E is equal to the integral over a closed loop of the electric field dotted with the area dA. Yeah, I will dissect this integral, don't worry. So we will simplify this later on. Okay, so this one is a dot product. Okay. The dot product is defined by a cosine theta function, right? So you can essentially write this down as the electric flux is equal to the integral of E cosine theta dA, eliminating that dot product. Theta, of course, is the angle between the electric field and some vector dA, right? What is vector dA? I will define that in the next slides. Right, so this is the definition of Gauss's law. It involves the electric field, and that's why it allows us to calculate the electric field of a symmetric object, right? So now what is this electric flux? This is a new term that we encounter, right? So the electric flux, this is defined as the number of electric field lines that's crossing a surface, right? Right. It's simply adding how many field lines are crossing a surface that gives you the electric flux. And if the electric field is uniform, okay, electric flux is defined by Gauss's law. If the electric field is uniform, then the electric field is constant. The angle is constant, and therefore we can just bring everything out of the integral. So you have E cosine theta integral of dA, and integral of dA is equal to A. And therefore, for a uniform electric field, the electric flux is defined as the electric field times the area times cosine theta. If you think about it, this definition sort of makes sense, right? Because say, for example, these are your electric field lines. Just imagine there is a charge at the back of this board, and this charge is creating an electric field line around itself. The electric field lines are shown here, right? So these are the electric field lines created by the charge behind this board. Electric flux is the number of electric field lines crossing a surface. So say if you want to find the electric flux through this surface, you simply count the number of electric field lines crossing the surface, right? So 2, 4, 5. But the number of electric field lines crossing the surface depends on how strong the electric field is. Hence, you have E. Okay, stronger the electric field, the more electric field lines, the weaker the electric field, the lesser the field lines, right? So electric field flux depends on how strong your electric field is. It also depends on the area of the surface for which your electric field lines cross. Because if you have a smaller surface, then probably only a few field lines will cross that surface. Right? And it also depends on theta, which is the orientation of the surface. If your surface is oriented this way, then you can think of all the field lines crossing the surface. Then you have maximum flux. If your surface is oriented this way, then none of the field lines will cross your surface, the surface. Hence, the electric flux will be 0. Okay? And all other angles will have variable electric field lines crossing. Right, so this definition is sort of intuitive. What is the angle theta? Right, so theta, it's the angle between the electric field line and the area. And this example sort of emphasizes which angle you should consider. So say here you have this surface and you have the electric field lines crossing this surface at an angle 20 degrees relative to the surface. Calculate the electric flux through the surface if the electric field has a magnitude of 500 newtons per coulomb. Right, the equation for electric flux is this. Okay, we know the electric field, it's given the area you can calculate from the dimensions of the sheet, multiplying length and width. The angle theta, okay, the angle theta, right, it's not 20 degrees, okay, it's 70 degrees. Theta is equal to 70 degrees. Can you see why? Why is theta 70 degrees and not 20? Right, it's because of this definition here, where theta, so theta should be the angle between the electric field and the area. And the area vector we define using a normal vector that's perpendicular to the surface. Hence, right, this is your normal to the surface. Therefore, theta should be measured between the normal, which is perpendicular to the surface, and the electric field E. So if this is 20 degrees, then it makes sense that this is 70 degrees. Right? So if the surface is open, like in this example, you calculate the electric flux using this equation. But you can also enclose the charges. Say, for example, you have charges inside a sphere, as shown in this figure. If the charges are inside an object like a sphere shown here, you calculate the electric flux as the charge inside the surface divided by a constant called permittivity of free space. In essence, the electric flux is determined simply by how much charge is inside your surface. Right? If you think about it, if you have a charge inside your surface, this charge will create an electric field around itself, and the electric field it creates will actually cross the surface, the boundary of the enclosing sphere. And so each electric field line coming from the charge inside the sphere will cross the boundary of the sphere. And that's why it's sufficient to find how much charge is inside the sphere to determine how many electric field lines will cross the boundary of the sphere. Right? So say, for example, you have a cube and you have these three charges inside the cube. Right? Each charge is given here, positive 20 times the elementary charge E, or negative 100 times the elementary charge E. Right? The electric flux or the number of electric field lines crossing this surface will be the total charge, okay, which is negative. So the total charge here will be negative 70 times E. You have a negative net charge. So electric field lines will terminate at your negative charge here, but each of the electric field lines terminating at the negative charge will cross the surface of the cube, and therefore the number of electric field lines crossing the surface of the cube is negative 70 E divided by the constant epsilon naught. Okay, are we still okay so far? So up to this point, we're just defining Gauss's law in order to find the electric field. So we still haven't used Gauss's law, okay, but we just defined how to find the electric flux, right? Gauss's law allows us to calculate the electric field of a symmetric object. In order to find the electric field, we need to determine what is the electric flux. We've just defined what the electric flux is. We can calculate the electric flux by determining how much charge is inside a closed surface. If we know how much charge is inside the closed surface, then we are able to find the electric field. Okay. Right, so let's look at an example to really see how to calculate that integral, how to simplify this integral and use Gauss's law to find the electric field. So we have here a point source, a point charge plus Q, and we've learned this charge will create an electric field around itself. The electric field is pointing away from the positive charge Q, and we want to find the electric field at point P, at a random point P. Right, we already know that the electric field is KQ over R squared from the definition of the electric field, but we want to use the Gauss's law to prove that the electric field is KQ over R squared. So how do we use Gauss's law to find the electric field at point P? Right, the first step is to enclose the charge. Okay? Because by enclosing the charge, we are able to find the electric flux that crosses through the closed surface. Okay, and which surface to choose to enclose the charge is up to you. It's up to you to choose which surface to use, but a wise choice will be to use the symmetry of the electric field lines. And I hope it's easy to see that there is spherical symmetry, right? You have, yeah. So if you enclose your charge with a sphere, because electric field lines are 3D, of course. So if you enclose the charge with a sphere, then you are able to find the charge, the amount of charge that's inside your Gaussian surface. Right, so enclose your charge using a surface. The surface you use is called the Gaussian surface. So Gaussian surface is essentially just the surface you choose to use to enclose the charge. Okay, using the surface that you've chosen to enclose the charge, you can define the unit normal vector dA. And usually if you use the correct symmetry, you don't have to worry about this normal vector, and you can just simplify the integral as E times A. So here's the secret, right? Which probably none of the textbooks will tell you. This integral here, you actually don't have to worry about evaluating that integral. As long as you've chosen the correct symmetry to enclose your charge, okay, this integral E dot dA will always be equal to E times A. Because through this surface, the electric field will be constant, so you can take out the electric field outside of the integral, and it's just integral of dA, which is A, and hence this integral will be equal to E times A. Okay. A is the area of the surface that you've chosen to enclose the charge. We've chosen here a spherical surface, and the surface area of a sphere is 4 pi r squared, and hence area is equal to 4 pi r squared. R is the radius, is an arbitrary radius of the sphere you've chosen. So this is the left hand side of Gauss's law. Okay, for the right hand side of Gauss's law, just look at what is the charge inside the surface that you've used. There is a charge plus Q. So charge enclosed is equal to small q. And so this is the right-hand side of Gauss's law. Left-hand side is equal to right-hand side. Hence, you have E times 4 pi r squared is equal to Q over epsilon naught. Simply rearrange this to find E, which is what we want to find. E is equal to Q over 4 pi epsilon naught r squared. And 1 over 4 pi epsilon naught is equal to K, right? Epsilon naught is just a constant number. If you multiply that with pi and multiply that with 4, you will get 9 times 10 to the 9, which is the value of K, right? And hence we get the same as the definition of electric field for a point charge. All right. Did I confuse you enough? Yeah, all right. And unfortunately, we run out of time and we're just in half of the lecture. But, you know, Gauss's law is really, you know, when I should probably say this off the record, but when I was a student, this integral really did my head in. And that's why I wanted to explain this quite carefully. So we will continue tomorrow's lesson, again, looking at 2 more examples of Gauss's law. And hopefully I will convince you that this integral will just be equal to EA every time. So I will see you in the lecture tomorrow, and have a good day, everyone.